Scientists have created a new type of superpolymer that could transform the healthcare and clothing industries. The polymer can lift 1,000 times its own weight and be programmed to hold a temporary shape until it is triggered by heat to return to its original form. By altering the number and types of molecular linkers that connect individual strands, researchers were able to adjust the material's stability and set the point when the shape change is triggered. The research team led by chemical engineering professor Mitch Anthameton at the University of Rochester created a material that undergoes a shape change that can be triggered by body heat alone, opening the door for new medical and other applications. Tuning the trigger temperature is only one part of the story, said Anthameton. We also engineered these materials to store large amount of elastic energy, enabling them to perform more mechanical work during their shape recovery. The first step in designing this material with shape-shifting power was to identify how to control crystallization that occurs when the material is cooled and stretched. While the material is in a contorted shape, polymer chains are locally stretched and small segments set themselves in the same direction in small areas, or domains, called crystallizes, which fix the material into a temporarily deformed shape. As the number of crystallizes grows, the polymer shape becomes more and more stable, making it increasingly difficult for the material to revert back to its initial or permanent shape. By including molecular linkers as a way to connect the individual polymer strands, researchers figured out how to tune the trigger temperature. Anthameton's group discovered that linkers inhibit but don't stop crystallization when the material is stretched. By altering the number and types of linkers used, as well as how they're distributed throughout the polymer network, the Rochester researchers were able to adjust the material's stability and precisely set the melting point at which the shape change is triggered. Heating the new polymer to temperatures near 35 degrees Celsius, just below the body temperature, causes the crystallizes to break apart and the material to revert to its permanent shape. Our shape memory polymer is like a rubber band that can lock itself into a new shape when stretched, said Anthameton. But a simple touch causes it to recoil back to its original shape. Having a polymer with a precisely tunable trigger temperature was only one objective. Of equal importance, Anthameton and his team wanted the material to be able to deliver a great deal of mechanical work as the shape transforms back to its permanent shape. Consequently, they set out to optimize their polymer networks to store as much elastic energy as possible. Nearly all applications of shape memory polymers will require that the material pushes or pulls on its surroundings, said Anthameton. However, researchers seldom measure the amount of mechanical work that shape memory polymers are actually performing. The polymer is strong enough to lift an object 1,000 times its weight. For example, a polymer the size of a shoelace which weighs about a gram could lift a liter of soda. Anthameton says the shape memory polymer could have a variety of applications, including sutures, artificial skin, body heat-assisted medical dispensers, and self-fitting apparel.